So yeah, my name is Lev. I'm an NLP engineer at FullFact. There'll be 3 parts to this talk. First, I will introduce FullFact. Then I will talk about specific NLP problem that I'm trying to automate. In the end, I'll talk about transfer learning. And if you're not interested in journalism or politics, then hold on till the end. There'll be some useful tools you can use at your work to solve your own NLP problems. Okay. So before I introduce FullFact, I'll allow others to introduce our work. So does anybody recognize this man? Yes? Okay. What's his name? David Dimbleby, yes. What does he do? He's a journalist. He's a BBC presenter. Every week he presents a BBC panel show called Question Time. It goes to different areas of the UK, and there local people from that area, they ask questions to politicians about something that happened that week. It's a political TV debating show. This is what he has to say.
There's a panelist tonight called FullFact. FullFact is an organization which specializes in fact-checking claims made by politicians and the media. So the panel had better watch out.
So yeah, what is it that FullFact does that the panel of BBC, Question Time should watch out? So first of all, we write fact-checking articles. So that articles on important issues in public life, and we always include links to primary sources. So we don't ask people to take our word for it. We allow people to check our workings, and we always show our workings in there. So if some of you had a week off and you wanted to research some particular public issue, that's the kind of work that you would do yourself. But we just save your time and publish a nice summary of that. But with links to all the primary sources, and you can go in this government published Excel spreadsheet and check it for yourself. Secondly, we submit corrections. If you find something that's been incorrectly reported, we try to stop it from spreading, and we go to the source and try to correct it in that original newspaper. We are the reason that several newspapers in the UK have correction columns. And thirdly, we work with people who produce the data, like the Government Statistical Service, for example, and we make sure that we help them to produce it in a clear way, in a way that can be interpreted in a way that has actually been collected and not prone to misinterpretation. For example, like we gave training to BBC on how BBC should present the data in their programming. Or like we have a project with Office of National Statistics to produce data in a machine-readable way, which a lot of people in this room can probably be excited. It would be nice if the data just came in not in a PDF, but in something which is an API. Wouldn't that be great? So organizationally, we are a UK's independent fact-checking charity. So we are funded by donations, and we are independent in terms of our funding. Like, there's no such thing as neutral money. Hopefully you'll agree, all the money comes from some kind of bias of it. That's why we keep our funding sources very diverse. Some of our funding comes from people, individual people who just donate £10 a month. Some of it comes from big charitable organizations like the Nuffield Trust. Some of it comes from corporations like the City of London Corporation or Rolls-Royce. Some of it comes from campaigning organizations like 38 Degrees. But none of them actually have a big proportion in our funding. That's why we can stay independent and have our own voice and not just do what the funders want us to do. Secondly, we are impartial. Political neutrality is very important to us. We keep a tally of the things, of the articles that we wrote based on statements of politicians and from which party they came from. So we try not to be biased in our selection of things that we write about. We're trying to stay neutral in our output. We also have safeguards at individual employees level. People who work for FullFact are very restricted in the political activity that they can do and political opinions that they can express. And thirdly, we have a board of trustees who come from politics and from outside of politics. Those of them who come from politics, they are from all major political parties. We have members of House of Lords from Conservative Party, from the Labour Party, from the Lib Dem, some cross-party members as well. And that way we can stay impartial, and that way that way we can stay neutral in our fact-checking work. And it's very important to be a source that people can trust in this kind of work. Thirdly, we are effective. We submit corrections for the work that we do. We also try to influence policy in the UK. We submit advice to policy decisions that are being made. And we try to change long-term the culture of public life in the UK. We would like to see a future where when you hear politicians say something on TV, you can be sure that it comes from a trustworthy source, that information that they're using actually comes from specific statistics which has been published, and anybody can check. That would be a nice world to live in, and to be a nice way to conduct public life in the country. Okay. So let me demonstrate what we do in one specific example. So there was, in April 2014, before the EU referendum, there was a TV debate. David Dimbleby was the presenter of the debate, and there was a debate between two politicians. And one of them said 70% of UK laws are made in the European Union, and another of them said 7% of laws are made in the EU. You can probably remember which one was which. And they spoke about it for 2 minutes, and then David Dimbleby said, okay, next question. And then they moved on. So, is it 70% or 7? Who thinks it's 70? Can you raise your hand? Nobody. Nobody thinks that 70% of UK laws come from Brussels? One person. Okay. 1, 2, 3, 4. Okay. What about 7%? Who thinks it's just 7%? Okay. A lot. Okay. That's interesting. So, wouldn't it be nice if there was some kind of database of facts? Would it be nice if just, I could look it up? It's 70 or 7. If there was just, one source of truth. We here at PyData London, we all want to use machine learning to change the world for the better. Surely the science can help here. There's a lot of things that we can do. Would it be amazing? And unfortunately, this is not yet possible. Unfortunately, even humans are struggling at this task and finding out what's true and false, what's black and white. We need really superhuman level AI. Maybe human level AI can do this, but superhuman level AI would probably solve this. So in 100 years, there'll be a nice database of facts, and you can, comfortably walk through the street knowing what's true and false. But right now, it's impossible, unfortunately. And let me illustrate on this one specific question. So according to research published by the House of Commons Library, the range here is between 13 and 62%. Any answer between these two is correct. So it's a 50% range. Your confidence interval is so big, And how can it be? How can there be these two big numbers? And the problem is that there's the word law here, and there's no mathematical definition of the term law. There are a lot of rules in the UK that we have to obey, and depending on which one of them you call law, you get a different answer. So if you look at the big fish, look at the things that are decided by Parliament, things that are signed off by ministers, and you look at how many of them mention specifically, we have to do it in the UK because the EU told us so, that will be 13%. So 13% of laws passed by Parliament or ministers in the UK explicitly reference the EU. That's one number. On the other hand, if I look at the small fish, if I look at quotas from imports of Moldovan milk, which are enforced on the territory of UK as part of the EU, if I look at this tiny half a page or maybe 1 page documents, that's where I get 62%. And these are the things which can be decided in UK maybe by a local city council. And there, in this comparison, I'm comparing a 300-page document establishing NHS to a half-a-page document about quotas of Moldovan milk. And I'm comparing them together. And they all both have equal weight in that comparison. So how do I compare one law to another? It's not, NLP engineer, of course, it's number of pages, definitely. But, it could be, impact on people's lives. And how do I measure that? So, unfortunately, that's very hard to answer this question. And that's a lot of fact checks. You read them, and it's okay, so which way is it? It's all very gray. And this is really a lot of our job is like that. We are inserting the shades of gray when politicians are campaigning in black and white. They have to say, in very charismatic, strong statements, and in reality, you have to give the whole posterior distribution, not just a point estimate, to use a statistical metaphor here. We tell you what the world is like, and it's usually complicated. Okay, so it is complicated. But I work in the automation department of Full Fact. I'm an NLP engineer. I should do something for it. And what should I do? And of course, finding out truth is a hard, difficult question. And there are more manual, more menial, more boring tasks that fact checkers do every day. And I should really focus on them and leave the difficult questions to humans and just automate the simple things. So what are the simple things in the fact-checking process? So this is the fact-checking process. First, we monitor. We watch this TV debate between two politicians, and this is a speech comes in. Usually, it's translated into text, and then in this text, I can spot claims. If I hear something that I wrote an article about 2 weeks ago, I can just tweet it out and publish it immediately. If it's something new, I can take a note, maybe publish it tomorrow or next week. So this is how it works. I monitor, then I spot the claims, write about them, and finally publish. So the first two steps are definitely automatable. I can convert speech to text nowadays in 2018 quite well, and I can extract claims from them. And this is what I will talk about in this talk, how to spot claims in text. The third step is automatable in some cases. If it's about number of laws, how do I automate that? Just any number between 14 and 62 is correct. That doesn't really tell the whole story, but there are some cases where it's very clear, like number of legal immigrants in UK in 2017. Like that statistic is available, it's machine readable, like I can do that, that's fine. Okay. So specifically the task that I'll talk about today is how to spot new claims. So input in my algorithm is a document, text, and output I want to highlight a list of claims in it, 1, 2, 3, 4, 4, 5, like the claims which are mentioned in that document. So we've done some research on this, and we found something about political TV in the UK. So we found we found the TV show that has the most claims. There's like one show where people just throw statistics around at each other, and this is pretty cool. So has anybody seen any of these shows, actually? Anyone? Okay, 1, 2. Oh, wow. I haven't seen any of them until I started working for Full Fact, so that's fine. If you haven't seen any, that's all right. Has anybody seen all 4 of them? Okay, a lot of political geeks in the audience. That's exciting. Okay, so which one do you think is the most heavy in terms of statistics? Like which one people throw claims around? Any suggestions? Yeah? Question time. Okay, 1 for question time. You think Prime Minister's questions is number 1? Okay. Any other ideas? Okay, so the top one could be Prime Minister's questions or question time. 2 options. Okay, so let's see. So Prime Minister's questions is the most heavy, so you're right. 32% of all sentences said in Prime Minister's questions are actually claims. Average Prime Minister's questions is about half an hour to 45 minutes. It's about 350 sentences in there, and a third of them are claims. So we get about 100 claims in the single program. Question time is below that, and the Andrew Marsh show is very, very far away. And this is average over 3 to 6 episodes, and I cannot show you averages, this is PyData. So of course it has to be a box plot. And this is a box plot. And this flavor of box plot that I use here is the black line in the middle, the dark line, is the median, so it is the middle of the data. The size of the box is bottom 25%, so the first quantile, and then the top of the box is the third quantile. And the whiskers, this ends of it, this is the minimum and the maximum. So, and the dots that you see on the screen, the individual episodes. Because for Prime Minister's questions, we looked at 6 episodes, and we manually annotated them. And we got a small spread for them. For question time, we manually annotated 5 episodes, and you can see a spread for them in there as well. For Sunday politics, we only did 1, and it's turned out to be quite low. It's only 8%, but I cannot report on it because it's not very reliable data. I cannot be spreading unreliable data. It's 1 show is not significant. Cool. Any questions about this amazing box plot?
It's very consistent, it's always around 30 for Prime Minister questions.
Yeah, they're in different leagues.
It's like they have a target assembly.
Yeah, I'm sure the producer from Minister's Questions has a target. Okay, so we annotated claims. I haven't really told you what claims are yet, and it's time to define it. So there's some nuances to what a claim is, but in black and white, it's a quantity. And it's usually a quantity in the past or present. You cannot fact-check claims about the future, unfortunately, but we can only talk about what happened in the past, and usually published by some government department. That's the kind of source that you usually check. An example is this government has spent £3 billion on reorganization of the NHS. And there are some numbers in the past which we cannot check, or just not interesting to check. If somebody says, I'm a qualified social worker, qualified for over 20 years, there's the 20 years as a quantity in there, but it's someone's personal history. It's only public interest, and it's not public information usually. So we don't check these things. So this is what we are looking for in the documents. This is what my algorithm should detect out there. And to collect these annotations, we use a tool called Prodigy. It's a self-hosted annotation tool. You don't have to go to Mechanical Turk or Cloudflower. You can just host it on your own servers. And it's created by the team behind Spacey, by Nes Montani and Matthew Honeyball, who created an amazing NLP library called Spacey. And this is an annotation tool. It was in beta in autumn. You should all check it out and use Prodigy. It's quite nice. It has different UIs. This is just one UI that you used. You can annotate images, different things with it. It has a nice, swipe left and right annotation interface, which is really cool. So this is a view, annotator's view. We recruited 80 volunteers to help us in this task. They just did it because they like full fact and would like to contribute. This is the screen that they saw. The sentence highlighted in yellow is the sentence you're supposed to decide on. The option number 2 is quantity in the past or present. This is most of the claims fall into that category, and then there are other categories in there which some claims belong to sometimes. You also see the previous 2 sentences, which are not highlighted in yellow. And this is a poor man's coreference resolution. A coreference resolution is when you see the word it, he, or she, you want to understand what it refers to. So here it says, what it is this. It takes people in Germany 4 days to produce. People in UK takes 4 days to produce. So what it is this. Like it here refers to the word challenge, the productivity challenge. And if I used neural coref or some other coreference library, I would have replaced it by square brackets productivity challenge. But I was too lazy to do that, and model doesn't always work. So I'll just give you previous 2 sentences, and that way you understand what the sentence is about, and just give you some context. And this is poor man's coreference that way. So we collected 25,000 of such annotations over 6 weeks. And every sentence was annotated 5 times. And I only looked at ones where we had good agreement. And we got 1,000 positive examples, 1,000 claims from this 12 hours of live TV. And we got 4,500 of negative examples, of things which are not claims. Most of the things that you hear in political program is actually not a claim. Whether it's good or bad is up to you to decide. Politics is not just about statistics. Politics is about ideology, people's beliefs, what's important. So it is fine. I'm not worried that there's not so much statistics on TV. But what I'm really worried about is that I have literally small data. Like my data set has 4,500 rows. This is not so cool. So what should I do? What do you do when you have a small data set? And the best thing you can do is steal, which is called transfer learning. So you find some problem which has millions of data points, and you train some model on that. And from that, well-trained model, you extract the core of it, just the core knowledge, the essence of it. And you take that part and apply it to your problem. You just finish it off with training on your tiny data set. That's what you do. That's called transfer learning. You train on what has a lot of data and apply it to something that has little data. So a lot of you has actually probably used transfer learning in NLP already. And in the form of pre-trained word vectors. So in the past, since 2013, there's a lot of pre-trained word vectors available online for you to download. There's Word2Vec, there's GloVe, there's fast text pre-trained models out there. Has anybody used pre-trained word vectors? Can you raise your hand? Okay, awesome. You probably use Google News, like this giant multi-gigabyte file. Or maybe you use fast text trained on Wikipedia, or something like that. So these are really good models. The problem is sentences. So claim is a sentence, and a sentence has 10, 15, maybe 5 words. And how do I get a vector for a sentence when I have 10 word vectors? What do I do? And the simplest thing I can do is averaging them out. There's some more advanced techniques like TF-IDF weights averaging, but the most naive is just averaging them out. And that's what we had to do so far. But it's 2018 now. There's a new thing called sentence embeddings. And there's a way to download sentence embedding from the web, and you can just plug them in, and you get some sentence meaning out. And it's called InferSent. It's in PyTorch. It's produced by Facebook AI Research, specifically Alex Conneau. And it seemed to work quite well on my model. So it's not just a paper. It's also a GitHub repo with code. You can see the PyTorch code behind it. And it's embeddings available to download for English language. And some papers come out and they have amazing results, but there's no code with them or no embeddings. And it means I have to spend, a week coding it and another $500 on GPUs to train this embedding. And this is annoying. This is really nice that Alex has shared the entire thing with us. It's also a bit risky because people can find bugs in your code and then report them. And there's some questions about some of the max pooling code in here. It produces different results in the paper, but still it's fine. Still everything works out. Just the numbers are slightly different. But I'm very grateful people put that stuff on GitHub. If you're an academic and you want to publish a paper, please put it on GitHub as much as you can. This is probably everybody agrees on that in PyData conference. So this is what InferSent looks like. It is a BILSTM. It's a very popular architecture. It's been around since 2005. I will talk more about architecture later, but like BiLSTMs have been used in NLP quite widely. Like there's nothing magical in here. And the max pooling last layer is also very simple. But I'll talk more about the architecture in a second. So first, let me talk about the data. Like what's the data that went to train this sentence embedding model? So the input layer here is the word vectors, and the GLAV word vectors that train on 840 billion words. So this is just common crawl. This is collected from a lot of web pages around the internet, from many years of crawling the internet. And this is unsupervised learning. You can train it on billions of words easily. Just if these two words appear together in my text of the internet, then it should appear together in my 300-dimensional vector space. That's where GLAV basically trains for you. And it is similar to Word2Vec, just academics like it more. It's a more explicit algorithm. There's less black magic in GLAV than in Word2Vec. So this is the input layer. Then there's a neural network. And this neural network was trained on a supervised task. And that's where they took 1 million of sentence pairs, and they compared them on a natural language inference task. I'll explain what NLI task is in my next slide. And then they wanted to see, is it actually universal? Like what the thing that you get, this in sentence embedding, does it work for all tasks? And they tried it on text categorization, sentiment analysis, and 10 other tasks as well. And they seem to do better than other architectures, better than convolutional neural nets, better than attention networks. The simple BiLSTM came out on top. And that's why they published it. So what is the thing that they trained on? What is this natural language inference task? And this is how they teach computers how to think. I mean, that's what the writing practice release is. But the thinking is quite simple usually. So given a premise, remember your logic classes, premise, hypothesis. So given the premise, 2 dogs are running through a field, how likely do you think is this hypothesis? There are animals outdoors. So is it entailment? Is it definitely true? Is it neutral? Might be true. Or is it contradiction? Definitely false. So which one do you think it is? So does somebody think it's definitely false? Might be true? Might be true. Okay, one person might be true. Okay, definitely true. Majority. Why is it definitely true? Can you tell me? Because the animals outside. Okay, yeah, like that dogs are animals. Fields are usually outside. It could be indoor field. Who knows? I don't know. But this is the kind of things that you want. If computers can solve these tasks, then they are thinking. Cool. So, specifically how this dataset was created is called Stanford NLI dataset. They took a large collection of photos called Flickr 30K. Then they threw away the photos and just kept the captions to these photos. And they showed these captions to people and asked people on Mechanical Turk to write out 3 sentences. So if you said sentences, 2 dogs are running through a field, you have to write 3 sentences out. One of them is definitely true, the animals outdoors. Second one might be true. Some puppies are running to catch a stick. It could be, 2 old dogs are running to their owner. Who knows? But it might be true. Or something definitely false. So the pets are sitting on a couch, this couch usually inside, and they're not running, sitting. So this is how this dataset was created, and this is what InferSent has been trained on, to think about such things. And this is the cutting edge of machine reasoning right now. It's like caption to a photo level, man is eating an apple, like this kind of things. Reasoning about such simple things which can be described by a photo. So it's not very advanced reasoning, but this is somewhere to start. It's a nice toy problem to train your models on. Okay. So first thing people notice when they look at this is that there are 2 ways to read a sentence. First you read it forward, then you read it backwards. So what happens here? So the sentence has 4 words. The movie was great. And you take the GLAV vector for every word. And the first layer reads it as the movie was great. The second backwards layer reads it as great was movie there. So it reads it backwards. And that sounds like cheating, like I'm telling the model the future. And so you read text forward and then you read text backwards. And of course, I don't read a book like that. When I read a book, I just go a straight line. And that's actually wrong. If people have done eye tracking studies on how people read, and if it's a sarcastic sentence, you go back and forth a lot of times because you just don't believe it and you just subconsciously read it back and forth. And some things that I say, for example, only make sense to you when I go to the end of my sentence. So it's actually how humans read. It's not cheating. It's a nice intuition about cognition that you have to go backwards and forwards that way. Cool. This is BiLSTM. The last layer here is called max pooling. And this is a way to create one fixed width vector from a sentence of 4 words or 10 words of 20 words. It doesn't matter how long the sentence is. My output vector is always the same fixed width. So how do I do that? Network produces 4 vectors, one for every word. They are the vertical ones with the axis in the graph. And I have to create one thing from them, regardless of the length of my sentence. And this is how max pooling works. Have a vector for there, which is 315, a vector for movie, 587, for was it's 101, so I have these 4 vectors. And the max pooling operation just takes the maximum in every dimension. So the first dimension, what should I choose? Out of 3, 5, and 3, I choose 5. It's the biggest in absolute value number. And for the second dimension, I choose 8 because it's biggest out of 1, 8, 0, 0. And that way I always produce the vector of the same length as my output of max pooling. And it's also quite nice because I can see where my maximums come from. In this case, they come from the words movie and great. So 2 of the bold numbers are in movie, and 1 bold number is in great. So these are the most important words in that sentence, And it does make sense to me. Like, there and was are just auxiliary things. I don't really need them that much. And you can make nice graphs from it. For example, this is a sentence, a man plays an instrument. An instrument and plays are the most important words here. If you have logistic regression on top of that, you can combine it with your logistic regression coefficients and see what are words in my positive class, what are words in my negative class. And you can add some interpretability to your algorithm. Cool. So coming back to my task, I actually tried this algorithm on my task of claim detection. And so just to remind you, I have a document coming in, and I want to highlight all the claims in my document. So the 2 metrics that I used are precision and recall. And easiest way to understand them is by understanding 2 types of mistakes that the model can make. First of all, it can say that chocolate is great is a claim. I wish that it was universal knowledge that I could, fact check that chocolate is great. I believe in it. I think all people should believe in it. But unfortunately, there's no quantity in here. It's not fact checkable. And maybe it's not good for you, actually. I don't know. And this is one mistake it can make. It's saying something which is not a claim can become a claim, and this is wrong. So your list of claims will be polluted. That would be noise. And second way it can go wrong is if it says that 350 million a week for the EU, which is the biggest claim here, the red bus claim, as it's colloquially known, is not a claim. It's something which is obviously a claim has been mislabeled as a claim. So the first one is called the precision mistake, where my results are not so precise. Like my output. Oh, okay, cool. And the second thing is called a recall mistake, is when there are some claims which did not make it to my list, did not make to the output of my model. And this is upsetting, which is something I will never see. My users want to see all the claims which are there in the document. So this is box plots again for precision and recall of several models that I tried. So the one in orange is InferSent, and this is the top one. So the sentence embeddings do actually work. Transfer learning does work. Okay, why don't I have one number? Why do I have a box plot again? And the answer to that is, why do I have a lot of numbers? Can anybody tell me? Yeah, cross-validation. I use 5-fold cross-validation. That's right. And that's why I have the spread. And it's usually like the mean is this black line in the middle, the dark line in the middle, and the whiskers show me the min and max of my range. So the recall is really wide. And why is my recall so wide? Has anybody been to Gail's tutorial yesterday? Yeah, on model validation. Okay, so you probably know already why recall is wide. But reason recall is wide is because I only have 1,000 positives in my test sample, and this is really small. My binomial distribution is really wide in here. There's a statistical reason for this. But main thing I wanted to find out here is how good is the sentence clever neural network compared to just averaging word vectors, something I would do last year. And it seems to do better. Orange is better than red in this graph. And it does do better. There's some signaling here. Specifically, InferSent is better than just naive word vector averaging. But if I do the Gail's calculation from yesterday, this is a slide that I had to add this morning, there's a way that they can actually be the same. There's the confidence intervals actually overlap. Because I only have 1,000 of positive cases, my range of the recall is actually 10% wide. And this is really wide. There's a way maybe they're both 89 precision and 79 recall. And in that world, I don't add anything by having this clever sentence thing. I could just be averaging my gloves. Yeah, so this is frustrating, but it just means that I need more data. But it is something that you should think about when you validate models. Cool. Any questions about this? No. If you want to have questions, just read Gail's blog. Yes, do you?
The question is, what classifier are you using here?
Yeah, so the question is, what classifier am I using here? And the classifier is just logistic regression on top of GloVe. The same one is I use on top of InferSent. So I'm working for a charity. Working for a charity is a bit like working for an open source project. In open source, you donate your time and skills, and you get out good tools in your ecosystem. The charity, you donate your skills and time, and you get good civil society in the country that you live in. And you also benefit from it as much as you benefit from good Python tools. So thanks a lot to these people who came and volunteered with us for several days or several weeks. And thanks to Andreas, who is our main annotator. And without his work, nothing would be possible. If you would like to volunteer with us, if your company allows you to take 2 days off to do some charity volunteering, yeah, come to me. We'll happily talk about it. So this is my conclusion. Transfer learning is really useful. It's worked really well in this task. It worked better than something I spent 3 days custom feature engineering. It's just something I downloaded from the internet, and it worked better than something I spent 3 days custom engineering. It was frustrating, but this is progress for you. Even parts of your job get automated. That is cool. Machine learning can make democracy better. It can help us spot claims and fact check them. It's not going to make it perfect. We're not going to solve all of our problems, but it will make it better. And if you'd like to help us, come to talk to me about volunteering, or you can donate at fullfile.org/donate. Yeah, thank you. If you have any questions. No? Question? Yeah.
So I'm interested in this transfer learning thing. How well does it perform when you need something domain specific? So say you've got something trained on all of Wikipedia, but you just want to focus it on, say, food. You'll have a lot of noise in that, in those embeddings. What can be done about that?
So the question is about transfer learning and how can it be trained in one domain, how to apply it to another domain. For example, Wikipedia, and apply it to food. So if you want to do sentiment analysis, and you train on Wikipedia, and Wikipedia is dry language, there's no emotion in there, you will never achieve anything. Models trained on Wikipedia have no emotion. Have you read Wikipedia? There's nothing there. There's a lot of emotion in the debating about editors, but there's no emotion in the actual article. So that's definitely not going to work. You have to there's not machine learning problem. You have to put your business analyst hat on to understand if there's actually signal in the data that's been trained on. The data that InferSent has been trained on is from Common Crawl, so just web pages, and it's quite varied, and it has a lot of different things in it, not just Wikipedia. I think that's why it works for my data, which is the news. And the natural language inference dataset as well, there's a new edition called multi-genre NLI, which doesn't just use captions, but uses other genres to train it on. But it's a very good question. You have to think with your human head, not machine learning head, is actually signaling what I trained on. Thank you. Yeah, I think there's a question over there.
I was wondering, you said earlier that when it's about feature claims, that you don't do it, but do you actually keep track of feature claims, and is there some ideas how to try to qualify feature claims?
There are organizations which specialize in future claims. They're called think tanks. This is the job. This is what they do. They predict. They try to influence policy in the future, and they try to have this, top-down approach. But we don't specialize it right now. There are a lot of claims now what will happen when we leave the EU, and all we can report is about current rules and regulations. So what are the current laws and regulations in place? But we don't say what's going to happen in the future. Just tell you from the current legal framework what would happen if it happened today. So it's really hard, especially in today's political debate in the UK. Thank you. Yeah.
Also about the future claims. Is your classifier able to distinguish the future ones out from the current ones effectively?
So one of the categories that we have in here is called a prediction. And that's how we can distinguish the future. Usually they have a verb in the future tense. It's not that hard as an NLP task to talk about, to distinguish is the future mentioned or not. So,
more of the annotation. How many, when do you reach a consensus for a particular sentence? How many tests or how many people need to vote on the particular sentence?
Yeah, this is a very important question. So it's the first time I was working with volunteers, not somebody who is paid to do annotations. So I wasn't sure how well they're going to do. So that's why I said, okay, every sentence has to be shown to 5 people. And if it's 3 people agree, then that will be a good signal. And it turned out that people who actually care about full fact enough to spend their time clicking on this are actually very thoughtful, and they spend a lot of time working on it. And next time I do it, I'll probably let it free is enough. Because actually people do it very carefully, much more carefully than they do it in Mechanical Turk for the minimal wage. But yeah, it's a very important thing to decide when you do an LP. Yeah.
Do you have some statistics on out of the vocabulary words? So if you have words that are not present in GLAV,
Yep.
if they matter a lot for identifying if you have a fact or not?
Yeah, that's a very good question. So GLAV is a fixed vocabulary technique. Once vocabulary is fixed and it's been trained on common crawl, there's nothing else that you can do. And this is very strange to me that people at Facebook use GLAV and not fast text, because fast text is much better at working out of vocabulary words. Fast text is a poor man's morphology. It works with chunks of words, like 3 or 4 letter context inside words. And if they trained that on common crawl, and with that trained InferSent, that would be much better. So if you have spare cloud credits, you should do that research and publish it, and I think it would be much better. But thanks for the point. No. Uh-huh. Yeah.
Did you try anything outside of max pooling, like maybe sec-to-sec or something like that?
This has been tried not by me, but by Alex Conneau, who is the author of InferSent paper. They also tried mean pooling, so just taking the mean of the 4 vectors. A lot of people try conditional random fields on top of it here, and that gives you sometimes 0.5% better if you can spend a long time to make it work. Yeah, but the other techniques that you can find, this is the simplest one, and that seems to work okay.
Question, please.
Last question, sorry.
So I have a follow-up on the question about agreement between So you mentioned people spend a lot of time, they're interested in this. So you probably don't want to do this with crowdsourcing, but you can also do it as a form of donation. So you ask people to provide you labels, and those who are interested will come and do the task. So
This is exactly how we did it. We did it in a newsletter to our supporters, ask who would like to take part in this annotation task, and I think about 150 people signed up. 90 of them actually logged in and did the annotations. So it was exactly how it went. It's a form of donation. People donated, I think it's like 300 man-hours that went into this so far. Yeah, this is how people support us. Thank you.
Right. Thank you very much again for the very interesting talk. Yes.